Let's continue with chapter 9 by looking at section 9.5. Now we're going to move from some of the previous combinatorial concepts into something called a combination. Now, combination, really what I'm doing is I'm trying to pull a subset. Now remember, sets do not have order. So I'm trying to pull a subset that actually have specific order. So with this idea, if I have n things, I'm going to choose r of them, where r is at most n, and both of them are maybe zero. Then R combination of n things is a subset of R of n elements. So another way to think about this, and I'm just going to kind of switch my shares for just half a second to a whiteboard. Is when we're looking at this, we can start to understand why we actually are kind of what we're looking at. So suppose for a second I have 3 items. Actually, we'll go with 5 items. So if I don't care, they're just 5 items in a giant bubble. I don't care the order, they're just there. If I want to pick 3 of them, so let's say I pick these 3, that's one way I could have picked the 3 of them. I could have also picked this first one, the second one, and the third one. I could put the first one. There's so many different ways to have done this. The question is how many ways then? This would be an example of picking 5 things out of 5 things, picking 3 of them. And the notation we use for that is what's known as the binomial coefficient. And it's this where you have brackets and you have 5 on top and the things I'm picking 3 on bottom. This right here is the value for which we are going to use. Now let's go back and I'll show you again what that looks like in the PowerPoint. All right, so continuing on, as you can see right here, we have the exact same notation, n choose r, because I'm taking n things and I'm choosing r of them. So let's kind of work through some examples and look at these. So the first one is I have Ann, Bob, Sid, and Dan. I know they're alphabetical. This is classic, actually, not just in combinatorics, in cryptography, and a lot of things we name things with letters. And each subset of size 3 is a 3 combination, or sometimes just we write 4 choose 3, because I have 4 things choosing 3. So let's look at all the possible different ones these, and let's look at what that is. Again, we'll talk about that. So here I had Bob, Sid, and Dan, left Ann out, and so forth, because I was choosing 4, which meant in each situation I was really choosing who do I leave out. So one interesting thing here is choosing who I wanted in was the same as choosing who I didn't want. That's an interesting note, by the way, for combinatorics. It isn't always easier to count what we want. Sometimes it's easier to count what we don't want. All right, coming back here, in how many ways can the people in the set form a committee of size 3? Well, we already did this. So we can actually do 4 ways to pick a committee of size 3. So this is the idea behind all this, that we can possibly do it. Now, a key thing here up to this point in time is whether or not we have order. If it's ordered, then not only do the elements chosen matter, but the order in which we choose them matters. However, and that is more leaning more towards permutations, because permutations deal with ordering. Combinatorics, combinations is dealing with unordered sets. So if we have something that's unordered, then we just have to identify the things that are ordered. But that means we cannot include order or else we're over counting things. And so the combinations are typically unordered and permutations are more ordered, but these are not simple one size fits all. I could give you a million problems that one of these formulas doesn't even fit, but combinatorics is just the process of thinking about how do they count. So let's think about this, come back here, and how could we have counted this? Because I'm going to give you the actual formula in a minute. So if we have 4 things again, but I want to pick 2 of them. Now let's just look at how many ways there are to do that. So remember we picked 4, there was 4 ways. We simply say, well, how many ways could I not pick the last one? Well, this one, how many ways can I not pick two is the same way as how many ways I could pick two. So it's kind of the same question. So let's just brute force it. And you can do this because it's really small. And we can start looking for a pattern. So we could have picked zero, all the sets with zero, then all the sets with one, then all sets with two. And notice though, I picked 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3. And that exhaustively gives me 6. Hmm. So 4 choose 3 was 4, but 4 choose 2 is 6. Well, that's interesting. And this idea, we can start thinking about why does this actually work out? It's because when values are small, it's easier to compute the complete values, all the possibilities. But when those get larger, by the way, this process of brute force becomes extremely hard. So you have to start thinking about it and even computing them on a computer because we're using what are called factorials. Those grow so fast that they quickly override everything. Even on a computer, you can put in a binomial coefficient that will crash a computer. Just fair warning. Don't try it, okay? So this is something we don't really want to mess around with too much. So we gotta kind of be careful to do this. So in order to show the formula, let me just go back to this for a second. I want to demonstrate an idea to help you really understand it. So a way to think about it is I'm picking two elements. So I have element one and element two, and then we're going to act like they're ordered. I know I want unordered, but let's just act like they're ordered. So I have four different options for the first one and three different options for the next one. So we'd often think about multiplying these together, and that's going to give me 4 times 3, which is 12. But the question is, let's say I pick, so four ways to do this. I could have obviously picked 0, 1, but I've also could have picked 1, 0. So notice I could, once I picked the two numbers, I could have, I have to undo the order. And so the way to do that is to literally divide by 2 factorial. How many ways could I undo it? Because I'm double counting essentially all those ways. So this is 12 over 2 factorial, which by the way happens to equal 6. Huh, that's our magic number. Let's go back to the previous example where we had 3 things and we're trying to choose 1. So again, I'm going to clear all that. And in that situation, we had 3 values. We could have put 4, 3, and 2 in this first spot. And if you do that calculations, because I would have ended up with 24. Okay, that seems really big. But I have 3 things underneath it. So I have to do 3 factorial to undo the ordering of that. This 3 factorial is to divide by it is to take away the ordering. And so this would be this over 3 factorial, which a reminder is equal to 6. So that's 24 divided by 6, which is 4. So the pattern you might see here is this one is 4 times 3 times 2 over, I'm going to get crazy here, 1 factorial times 3 factorial. Or I could have even just taken the top and I could have rewritten it. Let me erase this portion as simply 4 factorial. Well, what's the relationship of 4 factorial and 1 factorial and 3 factorial? Well, 1 plus 3 happens to equal 4. And that is the very essence from which we can build our formula, which is namely, and again, I'm ignoring this top one. This is the formula normally, and it's the n factorial. How many ways are there to do it if there was order? So let me undo this quick. So this portion of it is how many ways are there to do it if there was order? And then I'm simply dividing out the order. This lets us actually attack these problems much, much more effectively and much more powerfully. So we have lots of different options, and we're going to use this kind of process to work through all this. All right, so let's do an actual example. Consider the problem of we're choosing 5 members from a group of 12 to work as a team on a project. How many different 5 person teams can be chosen? Well, the answer to this is simply going to be 12 choose 5, which if you go through all the calculations, because this 7 factorial is going to cancel with the 7 factorial. 4 times 3 is 12. 5 times 2 is 10. So that's why those things cancel out. And we get 11 times 8 times 9, which is 792. This is exactly how we can move through this process and look at all the different teams that we have to deal with. Let's look at a different problem. This problem is we're going to actually deal with a lot of things in combinatorics and probability, deal with gameplay. And that's not because you're going to apply them most in gameplay. Well, you could. There is a number of mathematical jobs out there that are involved in poker and other gambling institutions, including designing slot machines and so forth. But there's also a lot of just examples that are easy ones that may seem more familiar. So if any of you played with a 52 card deck, standard card deck, there's a number of things. So we have a couple of situations, just get you familiar with some terminology. A royal flush is when you have 10, jack, king, queen, and ace, all the same suit. A straight flush is you have 5 cards of adjacent values. So ace can be high or low, and they have to have 5 numbers that are all in a row, and they have to be the same suit. By the way, this is the ordering in which they are considered most valuable. So royal flush is the hardest to have. A straight flush is next hardest, and then 4 of a kind. So obviously 4 cards of the same value. We don't care what the 5th one is. So in other words, 4 3s or 4 10s or 4 jacks, 4 kings. Full house means 3 cards of one value, like 3 kings, and 2 cards of another value, like 2 5s. A flush means all the cards in your hand are of the same suit, but not necessarily of the same order. So it's not a straight, it's not a flush. A straight means the cards are in a row in terms of their value, but not necessarily the same suit. 3 of a kind is 3 values the same kind. We've already mentioned it. 2 of a pair, 2 pairs, 1 pair, and no pairs. And no pairs, if you're playing poker, by the way, it's high card wins. So here's a question. How many 5-card poker hands contain 2 pairs? So we can break this down with a set of normal questions. Set 1, let's pick the 2 denominations for our pairs, because I have to pick 2 values or 2 denominations, whatever you want to call them, for your pairs. So they could be, I could pick ace and 5 or 3 and 8. There's lots of different options. But I'm going to choose those 2 different things, which that is going to be 13, choose 2. Then I'm going to choose 2 cards from the smaller grouping. So let's say I choose an ace. Well, there's 4 aces and I have to choose 2 of them. But I'm going to do the same thing again for the other value. And then I have to choose the last card that's remaining, which now I have to eliminate all the other values I've had. So there are 44 cards left because I took out 8 cards because it cannot be any of these 8 cards. So 52 minus 8 is 44. I'm just choosing one of those. So again, this is going to be 13, choose 2, choose your 2 values, then choose the cards inside those values, and then go from there. That's one way to do it. Truthfully there's other ways to have also done the same thing, but we'll just leave it here at this. All right. Second question, if you have a 5-card hand is dealt at random from an ordinary hand, what's the probability that a hand contains 2 pairs? Now, remember, probability is how many total you have over how many that you want. So we take 52, choose 5, and that is going to be our denominator, and the numerator is going to be this value right here, which turns out to be 123,552. Yes, there is over 2.5 million possible hands, and this is why it becomes massively problematic to deal with this. It's not including that when you actually play in a lot of places, you have mixed decks and other things like that, where you don't just have one deck, you have multiple decks, and things get even weirder. Probability changes nonetheless. All right, so this is an example. I hope that helps. Let me know what questions you have.